free fall. You need both of these papers to do it. Cut off the border and cut out every box. All right, so free fall. When you hear the word fall, what do you think of? Falling, okay. What do you think of when you think of falling?
Going down, something dropping.
Something dropping, going down. Okay, so I'll ask this question. What causes things to fall? Gravity. All right. So that is the key thing here. You need to keep that in mind when we're talking about this, that the reason things fall is because of gravity. So let's just make that our first note. Gravity makes things fall. All right. Now, how many of you ever watched a video of skydiving? Anybody ever been skydiving? Okay. I personally would never want to, but that's just me. All right, so skydiving. Ever watch a movie where they're skydiving and like they're having a conversation or they're yelling at each other during their skydiving?
Yeah.
You can't actually hear each other. It's way too noisy. There's way too much noise. Why?
Because you're going down fast and all the air's hitting you.
The air. Okay? The air is going by so fast and it's making so much noise, you can't even hear yourself talk when you're skydiving. Okay? So, when something is falling, air is going to interfere in its falling. Okay? Can you imagine yourself skydiving? Can you feel the wind hitting your face as you're going down? All right, think how strong that is, that wind hitting your face. It's like sticking your head out of a car that's going like 80 miles an hour. Okay? Can you imagine the wind in your face? Okay? So, when we talk about free fall is a physics concept where we pretend that there's no air. Because when you add air, it gets complicated. Okay? So free fall, when we say free fall, we assume there's no air resistance. Okay? So go ahead and glue that in. Now, assuming there's no air resistance, all objects fall at the same rate of acceleration. So, what does that mean?
So like you go like a water bottle lots into.
Yep. So, my favorite example. Okay? I have this huge heavy bolt and a marker. Similar shape, which means as they fall, air will have a similar effect on them. Okay? As they fall, air will affect them the same way because they have a similar shape. If I take these two objects and I drop them together, they fall at the same rate. Did you all see that?
Yes.
Okay? They fall together. So, it doesn't matter how heavy the object is, how much mass it has. What matters is what its shape is. If you don't believe me, take a piece of paper. Any piece of paper. Okay? If you take a piece of paper and you drop it, does it fall straight down?
No.
No. It kind of flops back and forth, right? If you take two, what?
Because of the weight.
Why does it flop back and forth?
Light.
Shape.
What makes it flop back and forth?
The air.
The air. Okay? Now, two pieces of paper, exact same mass. Do we agree? Or extremely close? If I take one and wad it into a ball and leave the other one flat and drop them both at the same time, which one hits the ground first?
Ball.
You already knew that. You don't even need me to see you do it, right? Why?
Because it is a circular And the air's not going.
Because the shape of the flat piece of paper catches the air a lot more than the wadded up piece of paper. So it's not the mass that determines how fast an object falls. It's air resistance, how much it catches the air as it falls. Does that make sense? Yes? No? Maybe? Okay. So when we're talking about free fall, we're going to assume there's no air. Guess what? If there's no air, parachutes don't work. I take the two pieces of paper, the wadded up piece of paper and the flat piece of paper. If there is no air, aka go to the moon, on the moon there is gravity, a lot less gravity, but there is gravity, but there is no air. No air, drop them, wadded up piece of paper, flat piece of paper at the same time, they will fall together and hit the ground at the same time. If I were to go to the moon where there is no air but there is gravity, and I take my big heavy bolt and my little lightweight marker and I drop them at the same time, they will fall together and hit the ground at the same time. Okay? Just like they do here on Earth. Okay? Yes? Do we understand what I'm saying? Okay. So, for all these examples, all this practice we're going to do on paper about falling objects, we're talking about free fall. Okay? Now, we have this very special number when we're talking about falling objects. Negative 9.8 equals, negative 9.8 meters per second squared. A very, very special number. Why is that number special?
That's gravity.
Very good. See that little lowercase g right there? We say this is gravity. All right? So, it is actually the constant rate of acceleration of falling objects at the surface of Earth. Okay? That's what it actually is. Take that piece of paper, a little bit of glue, glue it to the right side of your page there. Now notice the units. It's 9.8 meters per second squared. What do you know about meters per second squared? Those are the units for acceleration. Now notice this is a constant rate of acceleration of objects falling at the surface of Earth. If I take you to the surface of the moon, it's like 1.7, I think. If I take you to the surface of Jupiter, it's like 22 something. Okay? So, this number, gravity, only applies to the surface of Earth. There's still gravity in other planets, it's just a different number. Okay? So when we say gravity, we're talking actually about gravity on Earth, which for probably everyone in this room, unless one of you really has, dreams of going on to NASA, this is the only gravity you'll ever know. Okay, unless you become an astronaut.
Can't you pay to go to space?
Yes, it costs millions to go to space. And I think it's just like a quick trip. So, a couple hours, I think.
Just hours?
All right, so this little piece of paper here, often rounded to negative 10 meters per second squared to make easy estimates. Look at the number 9.8. It's almost 10, right? Like think about like $9.80. That's almost 10. So put this little thing right there. Okay? It's often rounded to 10 just to do quick, easy mental math estimates. All right? Now, my last question. What's up with the negative?
There's gravity.
Bingo. Remember we talked about positive and negatives with velocity? They tell you what direction you're going? Yep, that negative right there. That's because it's going down. Gravity makes things fall down, not go up. So, it's a negative number. Okay? So, you have to remember also when we're doing these problems, a negative velocity means it's something that's moving downward. Okay? Alright. So, what does this all mean? Okay, so let's see here. Take this piece of paper, little picture of our, okay. Glue it in on the left side there, your page. Okay. She's dropping the ball, and it's falling off the edge of the cliff. Okay? We have a free-falling object. We're going to assume that there is no air. In this situation, if we assume that there is no air, okay, it will fall at a constant rate of acceleration of a negative 9.8 meters per second squared. Now, before we go any further, I want to back up and review exactly what it means to accelerate. Okay? So, if we're talking about acceleration, something that's going faster and faster and faster and faster and faster. So right here, this worksheet we've done before. The car. Its velocity is going 0, 10, 20, 30, 40. Okay? It's going faster and faster and faster. It is accelerating at a rate of 10 meters per second squared. Every second, its velocity increases by 10. Do you see that?
Yes.
Does that make sense?
Yes.
Okay. Well, take that idea, and you see how it gets goes a little bit further every second? Take that idea and make it vertical. That's what we're seeing right here. Okay? It's accelerating. Every second, its velocity is going to increase by the same amount. So, right here, where the ball is in her hand right there, draw a little line. Write V subscript I, little I. In parentheses next to the I, put a 0. The initial velocity of the ball. So, if you're holding an object and you're just about ready to let it go and fall, what's its initial velocity?
0.
All right. So initial velocity, 0 meters per second. Now, once you've let it go, it begins to fall. Put velocity and then down below in parentheses, 1. So its velocity, its instantaneous velocity, 1 second after it has begun to fall. What is its instantaneous velocity going to be 1 second after it has begun to fall? All right, so what does acceleration mean? Every second it's going to increase by 9.8. So it's going to go from 0 to 9.8 meters per second in 1 second. Now, what direction is the ball going?
Down.
Downward. So, it's a negative 9.8 meters per second. Okay? Let's talk about the instantaneous velocity at 2 seconds. So, it has been dropped at 2 seconds, exactly 2 seconds after it has begun to fall. What is the instantaneous velocity of the ball? Okay? So, if it increases by 9.8 every second, it goes from 9.8
It's going to be a bit faster.
to 19.6. because 9.8 plus 9.8 is 19.6.
So it's going to be going up like that?
Yep.
9 seconds?
Also negative or no?
It is also negative because it is going downward. Okay? Instantaneous velocity at 3 seconds. 19.6 plus 9.8 is going to increase by 9.8. During that second, we get 29.4 meters per second, negative for downward. Okay? Instantaneous velocity at 4 seconds after it's begun to fall. So, take the 29.4, add. What am I going to add? 9.8. You get 39.2 meters per second, negative because it's going downward. Okay? And then our last measurement right there from the picture, velocity, instantaneous velocity at 5 seconds is 49 meters per second, negative.
What?
49. 49.0, 49. Okay? So, it's going faster and faster and faster and faster and faster. Make sense? Yes? It is accelerating as it falls. Okay, so we still have 4 more pieces of paper to go. But what can you tell all these 4 pieces of paper have in common? Formulas. So we're going to talk about the math. And we are going to do that on the OOPS page. So, without turning the page, go right there to the OOPS page. Do not turn the page, right there on the facing page. OOPS page. OOPS page. This is where we're going to continue on the OOPS page. Okay, so going through all those papers, grab one that says instantaneous velocity. Okay, when we are dealing with a falling object, remember we're talking about gravity. Gravity makes the objects fall. We all agree, yes? This formula to figure out the instantaneous velocity actually came from the original formula for acceleration. Acceleration is the final velocity minus the initial velocity divided by the change in time, where we replace the acceleration with gravity, and then we rearrange to solve for the final velocity. When you do that, this is the formula you get. Okay? When you do that rearrangement, this is the formula you end up with. Final velocity is gravity multiplied by the change of time plus the initial velocity. Okay? So, VF. Okay? So, when I'm talking about instantaneous velocity, that's what we were doing right here with in the picture. It's a question of how fast the object is going after it's been falling for a certain number of seconds. Delta T seconds. Whatever that delta T value is. So they might say, well, how fast will it be going if it's been falling for 5 seconds? Well, you can use this formula. How fast is it going after it's been falling by? For 6.73 seconds. That's the number you put in, the 6.73, that's your delta T. Okay? So, velocity. What are the units of measure for velocity? meters per second. What does the G represent? Gravity. And you're going to put in negative 9.8. The delta T, how much time it has been falling. VI, what's VI? Initial velocity, okay? Measured in meters per second. Now, a little note here about initial velocity. If you go back to that example we did with the girl dropping the ball off the cliff, what was the initial velocity? 0. Put here, the initial velocity is usually 0. Not always, but usually. So, you multiply gravity multiplied by the time, and then you add 0. Basically, it's just gravity multiplied by the change of time. Okay? So that's your first formula. Does it make sense? Can we use this? Do we feel comfortable with it? All right. Now, find this one. Displacement if VI is not 0. No, actually, change your mind. Put this one. Displacement if VI is 0. All right? Go ahead and glue that one in. Okay? The displacement if the initial velocity is 0. Okay? So if the initial velocity is 0, which is the usual circumstances, okay, we can figure out the displacement. What does that mean? Okay? If the question asks how far it has fallen, how far down has the object fallen, that's when we use this formula. Okay? The displacement. 1/2 gt squared. So, delta D, displacement. All right? The how far it's fallen. What are the units of measure for displacement? Meters. Okay? Now, the 1/2, you will just put that in the calculator, 1/2. What's the easy way to put in, instead of 1 divided by 2, what's the easy way to put 1/2 in the calculator? Write that down so you don't forget. When you go to put in the calculator, it'll be a lot easier. 0.5. All right, what's the G? Negative 9.8. What is the delta T? Okay, the delta T is how far it has fallen in number of seconds. So again, delta T seconds. If it says, how far has the rock fallen if it's been falling for 3.2 seconds? Well, that 3.2, that's your delta T. Okay? So, how much time it has been falling? Now, the last thing I really want to emphasize, the number one most common mistake people make when using this formula, you see that squared right there? Don't forget it. Yes. Don't forget to square it. Don't forget to square it. That's like the number one most common mistake everybody does. Even I make it that mistake. All right? Don't forget to square it. Now, a little note worth making here. All right? Your displacement, your answer will be negative. Why? Okay, because it's going down. All right? So we've talked about negative displacement before, going in the negative direction, okay? So if you look back here at the example, if her hand is the reference point, going up is positive, going down is negative. So from her hand, the ball is going to go in the negative direction. It's going to go down. So we're going to have a negative displacement just like we're going to have a negative velocities. Okay? So yeah, I should pick that note over here. Right here with your instantaneous velocity, that negative 9.8, your answer will be negative because it's going down. All right, what if my displacement is not 0? Dun, 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 dun. So I throw the ball downward, or I throw it up. All right, if that initial velocity is not 0, we have to use an extended version of this formula. Compare the two formulas, okay? This formula, this part of the two formulas is the same. This is added to it if the initial velocity is not 0. Now, if the initial velocity is 0 and you put 0 in here, it doesn't affect it. You'll still get the same answer. Okay? This is just a shorter version of the formula for when the initial velocity is 0. And because it usually is 0, it's easier. But if it is not 0, dun, 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 glue that in. Okay? If the initial velocity is not 0, all the same stuff applies. How far it has fallen in the number of seconds, our displacement in meters, our initial velocity is meters per second. Okay? Now, with that initial velocity, you have to make sure you pay attention whether it's a positive or negative. Okay? So put a little note here at initial velocity. Up is positive. Down is negative. So if you throw it up or if you throw it down, you need to make that positive negative distinction in order to get the answer correct. Okay? All right. Notice delta T is in here in the formula twice. Okay? And again, that's how much time it has been falling. Okay? And right there, the G, what's the G represent? Negative 9.8. And don't forget the squared. Don't forget the squared. Now notice I'm not putting the note, it will be negative. I'm going to leave that out there. Because if the initial velocity is not 0, depends upon whether you're throwing it up or down, and how fast it's going and how much time, lots of factors there as to whether that's going to be positive or negative. Okay? So I'm not putting that guaranteed to be negative. It might be positive, depending on the circumstances. Okay? And our last one, solving for time.
But if we don't have space
If you ran out of space, glue down. Put just a little bit of glue on one edge and glue it down like this or something. Just glue it, like, if you can, sideways. If you can't, just a little piece of edge so you can at least lift it up and see what's underneath. Okay? Okay. So, time. So in order to be able to do the time, you need to know both the initial velocity, the final velocity, and gravity. So it's going to give you a final velocity. How much time does it take to reach the final velocity? Okay? So our final velocity and our initial velocity, okay, both measured in meters per second. And G represents what? Negative 9.8. Oops, sorry. Negative 9.8. What's time going to be measuring? What are going to be the units for the time? Seconds. Okay. There you go.